Va. Nej. 10 gigabyte link. Ja.
Jag vet som mitt dömningsspel.
Visst att det kan vara dömning.
Alltså, det är 12 spelningar. Så det frivilligt på 1 poäng. Jag hade räknat 10 till 10 och vilket gör.
Ja, då börjar vi börja.
Let's go.
With facts that we can know about these vectors. If I call this vector, let's call it for now C parallel and C perpendicular. So the part of C that is parallel to the line and the part of C that is perpendicular to the line. What are their relation to C itself? Can I kind of set that up at this point? Why am I interested in being able to split the vector up, so to speak, into these two vectors? So can I set up a simple formula where I can, or an equation basically, can I set up an equation where I use all of these vectors and this equation is always true?
So you can see perpendicular.
Okay, C equals C parallel plus C perpendicular. Okay, I'm gonna lose these names here very soon. But yes, this is the idea. If I add this vector, because C perpendicular is here now, but I can just as well draw it this location since a vector doesn't have a location anyway. So this vector plus this vector equals this one. So I'm basically splitting this up in two. A simpler way of looking at this same type of projection is just setting up a simple coordinate frame here, or simple coordinate system, and to say, I have a vector, let's call it B. I have a vector B, and B equals Bx, By. It has x coordinates and it has y coordinates. I can also say this here vector is the vector Bx, 0, and this vector here is the vector, 0, By. And then I can say B equals the vector Bx, 0 plus the vector 0, By. So I'm basically splitting this up into x coordinates on the one hand and y coordinates on the other. Also I can say this vector here is the projection of B onto the x-axis, and this vector is the projection of B onto the y-axis. So what I'm doing here is I'm just expanding this idea. We know how we can split a vector up into its x-axis, or its x-coordinate, and its y-coordinate. What happens here is I'm going to expand it and say it doesn't have to be just the x-axis and the y-axis. I want to take any vector, or any direction basically, of this line here, L, and I want to say I want to use that as some kind of base direction, like I used the x-coordinate earlier. And I want to say, how can I split C up into its part that's parallel to this line and its part that's perpendicular? Just as here I said, the x-coordinate is simply what's parallel to the x-axis. The y-coordinate alone is what's perpendicular to the x-axis. Can you see how this helps me with the reflection idea? If we again simplify the reflection idea and say, how can I take a vector and imagine that it hits the x-axis and reflects off of it? This vector is x, y. Or let's just say this is now bx, by. If it reflects off the x-axis, what will the new vector be?
Like the opposite.
Bx, minus by.
Okay, so it's not completely the opposite. It's not the other direction. It's not minus b. It's going to be, so the vector that was on the way in, we basically retain the same x coordinate, right? But we just flip the y coordinate. So we get bx minus by. So this vector here is bx plus minus by, whereas this vector here on the way in, if we just draw it right here, is bx and by. All right, so this idea of flipping one of the coordinates in order to get a reflection, for it to bounce off of here and retain a natural direction. Can you see how finding x parallel and no c parallel and c perpendicular can help me do this not only off the x-axis, but help me reflect off of any vector at all? Is this idea kind of clear of what I'm trying to do? Okay, so we still haven't found c parallel and c perpendicular, but I'm just kind of laying the groundwork as to why we want to be able to do this. So in order to be able to reflect something off of something that is not just either vertical or horizontal, we want to be able to say, can I split this vector c up into the part of it that's parallel to this line, the part of it that's perpendicular to the line? Then I can take just one of those and flip it, and then I've got a new c that will actually look as if it bounced off of this particular line. All right. So now I'm going to change this just a little bit and say I'm now still going to look at the vector c, but I'm going to imagine another vector. This here is my vector v. So what I want to set up is some kind of equation or formula. Let's see, I can just erase this for now. We'll end up with similar images later on. I basically want to fill in this here instead of c parallel. Instead I want to say I want the part of c that is parallel to v. So what can I say about any vector that's parallel to v? Because we're basically looking at vectors and adding up vectors and scaling vectors and such and such. Any vector that's parallel to v is what? Or I can write it as, say here c parallel equals, how can I make that as some kind of formula of v? It'll still have unknowns, but I'd like to stick v in there. The vector that's parallel to v is just some scale of v. It's v scaled in some way. It's some multiplication of v. So if I can say, all right, I have some factor here, just a constant or whatever, just a numerical factor, and I multiply that with v, then I will have a vector that's parallel to v. I'm going to open the windows again. All right, if I then say, okay, I want to set up this formula here and say c itself equals some factor multiplied with v, which means that's some vector here. So this vector here is then k times v. So v can be any length there. But the vector that is exactly this length and also parallel to v, that's my vector k times v. But I want to say c equals some vector k times v, something that's parallel to v, plus something that's perpendicular to v. And we haven't really looked at the perp vector. We can say if I have v here, then v perp, drawn like this, is the perpendicular vector to v, and v perp equals that will be x coordinate here, yeah, minus v y, comma vx. And that would be a vector that's perpendicular to v, as if it was rotated 90 degrees counterclockwise, and it has the same length as V. So we can also say that the length of V perp equals the length of V. And that can be important as well. It's just V rotated 90 degrees counterclockwise. The perpendicular vector as well is only defined in 2 dimensions. So the perpendicular vector as such can't be used in 3 dimensions. However, any formula that we can get out of this, where we kind of lose the perpendicular vector idea, we can basically expand that into 3 dimensions as well. We'll look at that later on. All right, so I'm going to put some other factor here and say k times v plus m times v perp. So v perp would be here. This is v perp. But this vector here is m times v perp. In this particular case, as I drew it here, m will obviously be a negative factor. It'll scale it, but it'll also flip it. But that doesn't matter. This can be any way around. So we have m times v perp, we have k times v, and these two put together equal c. Do you feel like we're getting anywhere with this, or just writing a jumble of letters onto the whiteboard? So, without thinking about the math, like, what do you feel like I'm going to do with this? If I'm looking for my formula, that is in the end supposed to be the reflected vector equals such and such function of c and all the vectors that I have. Like, I need to find some way to take these unknowns here and make them known to me, so that I can just set this up as a formula with fewer unknowns. To begin with, does this, as it relates to the image, at least make sense? Okay. So what I want here is I want, as my next step, to be able to say, this holds true, where k equals something, and m equals something. So I want to solve for k and I want to solve for m. V perp, and c, they're not really unknowns as such in this formula here, in this equation. They're variables, certainly, so I don't have actual numbers for them, but they're not unknowns. At any time when I want to calculate this, I know what v is, I know what c is, because I have some particular setup that I'm calculating from. So c, v, and v perp are variables, whereas k and m are unknowns. So when I have 2 unknowns, how many equations do I usually have to solve for, like in the math that you've learned? 1, 2? Do you feel like you can solve for 2 unknowns with just 1 equation? Usually 2. So then let's go back to ideas about vectors, about vector math that we were doing last time. We were looking at the angle between vectors. We were looking at what happened when vectors were perpendicular to each other, and what mathematical functions gave us which values if they had a certain angle between them. Can you see any way where I can do something to both sides of this equation and simplify my number of unknowns? Can I possibly just lose one of the unknowns without making I mean, obviously you can always do something like, 0 times this equals 0 times this, and I've solved it, but I've lost both my unknowns and everything's gone, right? Is there something I can do where I can do something that retains the truth of this equation, retains my variables so I can calculate something from them, but kind of loses one of these unknowns? While you're thinking about that, we're doing this math now, but in the end we get a little formula from this. We get an equation or a formula from this, and then we can use that in our program. So I don't expect you when you program to actually program all of these steps. This is just our way to kind of get to the truth of how this little formula that we're going to use later on works, just to understand it better. So at this point, Can anyone see something that I can do to all of this based on the vector operations that we've been looking at so far, particularly the ones about angles between vectors, where I can lose one of the unknowns? Like, what is the relation between v and v perp? What is the angle between them? 9 degrees, so they're perpendicular to each other. What does that mean about their math? Two perpendicular vectors, they yielded a certain value from a certain operation. Do you remember this?
0 from the dot product.
0 from the dot product, okay? So v perp equals this. The length of v perp equals the length of v, and also v dot v perp equals, in every case, 0, since they're perpendicular to each other. So what can I do to this formula here? Can I say c dot v equals this entire thing dot v, right? This is a vector, and we can see that this is also a vector. This is a linear combination of two vectors. This vector scale gives us a vector. This vector scale gives us a vector. Two vectors added up gives us a vector. So we have a vector on each side of this equation. So I can take this entire vector here, and I can do that dot v. And I can do this dot v. So okay, I changed this. This also means that since we have already seen that if we multiply something with a scalar and then take a dot product, we can just as well have taken the dot product first and then multiplied it or then added it up. So we can say this equals k times v dot v. And so we know this is true. K dot v is a vector, that dot. We've also looked at the fact that we can just as well scale afterwards as we can scale beforehand. Plus m times v perp dot v. Okay, so what happens now? V perp dot v is always 0, right? So this entire thing disappears. So now I have one unknown, and I want to solve for this unknown. So I have k here, and what is k going to equal in the end? If I simply take this and divide it into both sides, so this entire thing divided by v dot v, k equals c dot v divided by v dot v. And what is v dot v also? Yeah, the length of v squared. So it just depends on what we're doing with this, whether that's a better way to set it up or this. Either way, c dot v divided by v dot v. So how can I do the same thing for m?
Use the dot product of v perp.
Okay, so I can do the same thing and I can say, okay, instead of doing this, I was gonna do this with v perp. So then I have here k times v dot v perp plus m times v perp dot v perp. Fine, so v dot v perp is 0, we lose this, and then what does m equal? C dot v perp divided by what? V perp dot v perp, which is also the length of v perp to the power of 2, which is also, all right, so v perp dot v perp, we can't just switch out v perp for v anywhere, but right here we have the length of v perp equals the length of v. So since this is the length of v perp squared, it's also the length of v squared, which means it's also v dot v. So we can simplify this and say one of these constants now, or one of these factors, is c dot v divided by v dot v. The other one is c dot v perp divided by v dot v. So then we can simplify this here. And just write this up and say c then equals c dot v divided by v dot v times v, right? Plus, to make this a vector, because these dot products just yield numbers. So this is just a number. This is just a scaling factor on v. So we have our scaling factor that if we multiply it with v, we get a vector that's parallel to v and is exactly the correct length to be the part of c that is parallel to v, plus c dot v perp divided by v dot v times v perp. Are we any closer to gaining a formula for the reflection? Can someone see how we could just from this kind of calculate that? So if we're going to reflect c off of this line, off of whatever line is parallel to v, we want c to come here and bounce off here. Retain the same speed as c had, or the same length as c had. We want it to be equally long to c, but just such that it has reflected off of this. Then we're basically taking the part with v perp, right, and we're flipping that. So we can say our reflected c, and I'm going to change this and simplify this actually, but for now we can still say, since the reflection is what we're looking for, our reflected c equals the part that's parallel to v, unchanged, minus the part that's perpendicular . Right? Does this make sense? We can take the part that's parallel to v and keep that unchanged. This vector here is unchanged. Then we take the part that's perpendicular to v and we take that in the other direction and say we're going to subtract that from it rather than add it to it, which should yield this vector here, c reflected. But still, this is a lot of calculations to do. We'd like to simplify this. We'd like to simplify this in two ways. Number one, we don't want the part with the perp vector to be what we're going to flip, basically, because we're going to want to lose the perp vector thing, because later on we want to take this formula that we get unchanged, this function unchanged, and be able to take it into 3 dimensions. And we also want to kind of see itself a stronger part of this formula in its entirety. So I'm going to start with the first one. And in order to do this, we're going to define, we're just going to switch over to the other half here. Here, all right. We're going to define more than one way of defining a line. So the line that we were looking at here was a line with 2 points. So we have the point B and the point C. Let's just look at this particular representation here. We have, let's call it now the point P1. We have a point P2. And we want to be able to represent somehow every single point on this line as some kind of formula. So we want to be able to take some kind of basically linear interpolation here between these points and say any point P, and I'm also going to look at basically the parametric form here. Any point P that we can represent as some kind of weighted average of these two, where I'm going to say I have some, let's say P as a function of T equals 1 minus T times P1 plus T times P2. This point will be on this line. So if I put some T in here, let's say I put the T 0, I'll get 1 minus 0, which is 1 times P1, and I'll get 0 times P2. So 0 into this parameter here, into this function, will give me exactly P1. A value of 1 into this function will give me what? P2. It will yield 0 here times P1 plus 1 times P2. Anything larger than 1 will be a point somewhere here on the line. Anything smaller than 0 will be something here on the line. Anything between 1 and 0 will be on this part of the line. So now I have a way to calculate points on this line. And this is what's called the parametric form. What's great about the parametric form as well is that I can split it completely into the x dimension equals 1 minus t times p1x plus t times p2x, and the y dimension, py times t equals 1 minus t times p1y plus t times p2y. So I can calculate this in the x dimension, y dimension, and this helps tremendously when we're programming these things, to be able to calculate these things completely independently of dimensions. All right, so we have this first parametric form of a line, or linear interpolation of a line. This is also called the linear interpolation of P1, P2, and T. We'll look at that later on, but it's nice to have it here. So we have 2-point form here. What I also want to look at is what's called array. So this is 2 points. Array is basically a point and a vector. I'm going to say I can represent the same line with a point P1, or in this case let's call it the point A, and a vector C that is parallel to this line. So how would my function for that, my parametric form, now look? P of t equals, again I have this parameter, which is just a number I put in there. I seed it with this number to get any point along the line. It would be A plus t times c, which is simply a linear formula here. So I have a nice linear formula for array. Again, if I put 0 as t, I get this point A. If I put in 1 in the parameter, I get the point which is exactly where a point would be if I moved the point A by exactly 1 vector c. So take A and move it by 1 vector c, I end up here. And this is what we're going to generally be using for objects that we're moving around in space in computer games. It's kind of, I have an object, I have a projectile, and this projectile is moving in a certain direction. The position of the projectile is A, the current position. The motion of it is C. And then every single frame I can say, how long was this frame? Well, I'm going to find a new point along this trajectory by saying the current position plus how long this frame was times the vector that it's moving along equals my new position. So that's how I move things along. All right, so here we have 2 points. Here we have array. And now my question is, if I want to change from the 2-point to the ray representation, but still retain the exact same line that I had originally. How can I do that? So here I have A and I have C. Those are kind of my variables. Here I have P1 and P2. So how can I calculate A and C from P1 and P2? A equals, does it? A is my point. Yeah. So that's true. C certainly equals P2 minus P1. So the difference between 2 points is a vector. If I subtract 1 point from another point, if I subtract P1 from P2, I get the vector between them. So this is the vector V, which equals P2 minus P1. So that's the relation between points and vectors. If I subtract 1 point from another point, I'm basically taking their difference. I'm taking how much would I have to move this point for it to become this point. How far away is this point from this point? And that is answered by a vector. That vector basically says this is how much you have to translate in order to get to here. And also a point plus a vector is just another point. That's me moving that point by this vector. What does A equal then? Yeah, P1. If it matters to us where it starts and we get the same, basically the same result from the same parameter, then yes, A would have to equal P1 in this case. If it just matters that we have the correct line and that we're representing this line in general, then it doesn't really matter. A can be P1 or A can be P2. No difference. Anyway, so this is us changing from the 2 points to the ray. What if I want to go the other direction? I want to find P1 and P2 from A and C. Then P1 equals A, and P2 equals A plus C. All right. A plus 1C, or just A plus C. So P1 will end up here, P2 will end up being exactly P1 displaced by one amount of C. Okay, this is simple enough. But what I want to add here, I hope it'll show up properly on the board here and on the screen, is I have one more representation. So I'm going to call the point normal form. Which means I want to represent this line by a point on the line. And here I'm going to call it B. And I want to represent it by a vector that's perpendicular to B. I'm going to see that this, yeah. Or perpendicular to the line, sorry. Obviously nothing can be perpendicular to the point. So I have this line, I want to represent it with a point B and a vector that's perpendicular to the line. This is interesting to me because if I take this formula here, or this equation that we end up in the point normal form, and expand it to 3 dimensions, then I can use it completely unchanged, but then it doesn't represent a line anymore, it represents a plane. Basically a plane which is something that the side of a polygon could lie in. If we imagine we have a polygon here in 3 dimensions, a plane is basically, if we expand kind of the angle of this polygon in all directions, that is basically the plane that this polygon lies in. Same as I can say, if I have 2 points here, then a line is basically, if I take the line between them and expand it in all directions, that's the line that these 2 points lie in. So in 3 dimensions this becomes a plane, but the point normal form is the same. So now, in 2 dimensions, I now have B and I have the vector n. And now my question is, if I want to go from the ray form and into the point normal form, I need to find B and I need to find n, and I have A and C. So what would B be? B is basically just any point on the line. Here we have a point on the line, which is A, fine. What would n be in 2 dimensions? C perpendicular vector of C. So basically take C here, make the perpendicular vector C perp, and that is n. So now I'm going to set up the actual equation for the point normal form. And the idea is this. Whereas here, I set up any point on the line in the parametric form as a function of A and C. I say I have a function of A and C, or actually it's a function of T, where A and C are kind of constants in it, or A and C are the factors here. So I set it up as a function of T, and I say if I send some T in here, it will return to me a point, and that point will be on the line. In this case, I'm going to set it up as an equation, and I'm going to say this equation is true if some point that I choose is actually on the line, but it's false otherwise. So I'm just going to take a random point here. I'm going to call it R. This is just some random point on the line, but I'm just going to set up an equation that always holds true if this point R is in fact on this line. So how could this equation look? Knowing what we know about vectors that are perpendicular to each other.
Dot product of R minus C to n is equal to 0.
Okay, R minus B it would be here. So I have the point B, I have the point R. If I take R minus B, right? R minus B would be this vector here. So this is the vector R minus B. If the dot product of this vector R minus B and the vector n, so n dot R minus B, if that equals 0, then these vectors are indeed perpendicular to each other, which means that the point R is on the line. So the point normal form is not something that's very simple to use directly in a program like this, where we simply kind of think about things as motion over time along this line. But it's something that can help us tremendously when we need to basically calculate certain formulas from lines that we have. And this is going to really help us, the point normal form, both when we're going to calculate intersections, and we're going to use it to begin with to kind of simplify a little bit our reflection as well. And normals, that is perpendicular vectors, is what we use generally all the time in lighting calculations and in things like that. Calling the normal to the vector, or normal to a polygon, sorry, in 3 dimensions is a very important asset of that, which really gives us the 3D feel in the end. All right. Doesn't much matter how I get back to here, but it's an interesting trick. Let's finish that. Start it here. All right. Let's finish that, and then let's take a short break, and then we'll really get to how this portrays to the reflection. Okay, so I have B and I have N, and I have A and I have C. Okay, in 2 dimensions it's not that tricky really. Basically say, A equals B, and then C equals what? If we want the same C back, calculating it from N. Perpendicular N, but do we then get the same C?
No.
Because N would then, or C, went back here. If we do the perp vector again, it goes here. So I guess flipping that vector, minus n perp. Let's finish this a little bit before we take the break, just to have this continuous here. So let's go back to these images, and I am going to change this image a little bit. Like so. And we're going to say, okay, I have a vector C, and I have this imaginary line here, but now I've represented this line with a vector n. So now I'm thinking about which part of C is parallel to n and which part of C is perpendicular to n. So this line is now represented with a normal rather than with a parallel vector. That basically means that we can just flip this. We can say the part, or this holds true still. We can still say, except we're going to change it to n here. Sorry, this is the reflection part. We can still say C equals C dot n divided by n dot n times n plus C dot n perp divided by n dot n times n perp. Except now this is the part that's perpendicular to the line, right? It's parallel to n, but being parallel to n means it's perpendicular to the line. So now this is the part that we want to flip. This is the part that's parallel to the line, so this is the part we want unchanged. So the question now is, earlier we simply said, okay, if this now equals minus this plus this, then we've got the flipped vector, and then we've got the C reflection. And I'm actually going to call it R in this case, and I'm going to change just the... Okay, I'm going to call this one A, which is the original vector. I'm going to call this vector R for the reflected vector. So I'm just using the same thing, I'm just changing the names a little bit. So the reflected vector equals minus this part plus this part. How can I lose this part? That is, how can I lose this perp vector here? Like, what is R originally? Or what is A originally? So we have two parts here. We have this part and we have this part. And A is originally the sum of these, right? So if I'm going to say, I'm going to take this part minus this part, in that way, so this part minus this part, that'll give me the reflected vector. Instead of taking this part at all, can I somehow use A instead? Like if I've calculated this part, how can I just subtract that from A and get the reflected vector? If I have A here, and I have the part of A that's parallel to some line, and I have the part of A that's perpendicular to some line. Like, what happens if I subtract this vector from A? I'll get the other one. Because indeed, this vector plus this vector is A. What happens if I subtract it again? If I subtract this vector from A once, I get the parallel vector. If I subtract the perpendicular vector again, what do I get? Reflection. The reflected vector. So I now want to say the reflected vector equals the original vector, which is A, minus what? minus what? Minus this vector. No, not this vector, actually, this one. A dot n divided by n dot n times n times 2. Now, can I simplify this even more? If I view this as the length of n squared, let's imagine that my normal is already a unit vector. Can I then simplify this? Then I guess this is 1, right? The length squared is 1. So I can say the reflection, if I'm so lucky that n is a unit vector, minus 2 times a dot n times n, then this is my formula. So I can simply say, if I just make sure that my vector is a unit vector before I start, just say n normalized, and I can simplify it like this. So I have one dot product, I have that dot product times 2, and I multiply that with my normal, and then I've got my reflection formula here. And in the image, it's basically this vector is n, this vector is a, this vector is r. So I can say by taking a and basically taking the part of a that's parallel to n. So imagine I have a here, I can draw it here just as I can draw it here. And then I can subtract this once, I can subtract this again, and then I've got the reflected vector r. So all I really need is which part of a is parallel to the normal n, subtract that twice, and I've got the vector r. Questions regarding this? This is basically our goal, our little formula. When you program this, nice to know how this works. But what you're going to do is you're just going to say, okay, I know something has collided. I know something has basically hit in a certain place. I know it hit an object that is tilted in the way that this is the normal to it. Also, if something that you have hits a sphere or hits a circle, comes in here, A, what's the normal to the circle? It's basically different in every place of the circle, but it's basically if you take the place that you hit the circle and subtract from it the center of the circle, then you have a normal that points straight out. So if I hit the circle, I know that this is the normal that I'm going to bounce off of. Since I know the normal that I'm going to bounce off of, I can just throw A, which is my original vector, and N, which is the normal, into this formula, and voila, I have the correct reflected vector of the correct length. All right, let's take a short break now. I know it's a little bit late for break. Let's take 5 minutes and see if we can at least start looking a little bit at the intersections as well.
Það er að fæla þetta í öllu vansu karakter. Það var í pandasokkum, það var í öllu skeitir.
Já, ok.
Veistu eitthvað að skeita það?
Já, ég gerði það miklu meira einu sinni heldur en ég gerði það núna.
Já, ok.
En wardrópið mitt litast fínar.
Það er að fæla þetta svona.
Já, ég skeitaði mjög mikið einu sinni. Ég reyni alltaf að koma smá hjólabretti núna á hverju ári.
Já.
En það er bara svona til málamynda meira.
Kannski er vera svona sem eldist 9 núna.
Já, það er nákvæmlega hjólabretti og BMX hjól eru heldur harðara sumarsíson.
Já.
Þannig að það er full fjöður í fjallahjól núna.
Hérna.
Það er ykkur án hérna.
Já, fjallahjól. Já. Hefur ekki maður tekið downhillið í Öspilið?
Já. Ég hjóla mjög mikið og hjóla mjög mikið þar. Og hef verið tekið aldrei þátt í að í hópnum sem græjar þessar leiðir og það dót sem er búið að gera það út allt.
Það var náttúrulega sko hörku BMX, nei hérna svona mountainbike park hérna sko, eða svona, hvað kallar maður það? Dirt jump.
Þú sem var dirt jump?
Hérna, eða sem hávar að byggðu sko, og það var reyður út því að það verður mikið hávar.
Það var svo leiðis að gera eitthvað pump track hérna náttúrulega líka, en það er bara að byggja. Það er líka að byggja allt.
Hérna, ég var að pæla, allt þetta, er þetta bara sem við erum að fara að testa á prófinu?
Sko, já og nei. Þessi formúla hérna, hún er klárlega eitthvað sem við erum að fara að nota í forriti til þess að skoppa hlutum. Þú veist, hitt að þekka hvernig dotproduktu það virkar, það er meira bara hlutir sem er að fara að vera í einhvern heimadægum á prófi. Meir og minna samt þá er ég ekki að prófa mikið í því að rekja þetta allt. Þú veist, að rekja alla þessa hluti sem ég er að rekja på töflur. Meira bara að nota formúlunar rétt, skilja gögnin sem fara inn í þær.
Eða þessi heimadæmi, verður þau alveg vikulega eða svona cirka?
Nei, þau verða 5 yfir önuna, alla. 5 heimadæmi yfir önuna.
Ég er bara spánablaður og ég er svona svolítið shaky í svona starfrækgreiningu og svo sko. Þannig að ég pæli hvernig ég geti best undirbúin fyrir prófið. Gera heimadæmin og það?
Já, basically. Gera heimadæmin. Ég seti inn fullt af gömlum prófum og alls svona dóti bara leysa þau dæmi, leysa þau verkefni. Við myndum byrja á heimadæmunum sem eru núna og bara komast í gegnum þau.
Við vorum að fyrir að leysa svona dæmi sem reflection online og það.
Já, ég var búinn að setja, það er í heimadæmunum núna sem ég var að setja inn. Ég var líka búinn að setja inn einhver svona practice examples og lausnina mínar við þeim og eitthvað svona þess.
Já.
Þannig að bara fara í gegnum það og skilja það. Komast svona þokkalega í gegnum það allt því að sé besti undirbúningur fyrir prófið.
Eitt varandi líka 2D leikning.
Já.
Er einhverjir standardar það?
Sko, ef það er eitthvað annað heldur en akkurat þessar hugmyndir sem ég er að setja fram, þá vil ég gjarnan vita af þeim. Bara því mér langar til að eitthvað svona collision detection og collision response, svona skopp sé í því. Eitthvað eins og Pac-Man til dæmis, það gerist svo mikið á gridi. Það er svo rosa mikið, þetta er bara hingað og svo tekur 90 gráða beygja og bara hingað, þú ert alltaf confined af þessu völundarhúsi, þannig að það er ekki beinlínis collision að gerast í því. Þannig ég myndi segja, það er óþarflega einfalt.
Já, hvað maður að gera svona eitthvað eins og asteroid eða eitthvað svona víkingu og því?
Já, það virkar alveg, þá ertu með einhvern hlut sem að hreyfist, einhvern acceleration, þú ert með einhvern projectile sem collide eða einhver öðru, það springur, það er svalt ef þú getur komið fyrir skoppin, þannig að ef asteroidar hittir hvern annan þá frekar en að þið fari bara í gegn, þá ertu bara komið með fínt svo.
Megum við nota, þú veist, ef það gefst tími að bæta inn, þú veist, myndum og...
Þið megið það, setja inn einhverja textúra og dót og svoleiðis myndir og eitthvað, en við förum í það meira seinna.
Er ekki seinna í að bæta inn hljóðið?
Sko, ég fer ekki sérstaklega í það, en ég skal alveg passa að sé einhvern efni, einhver resource til þess að gera það. Pygame býður þetta upp á mjög þægilega leið til að bæta inn hljóðið.
Bjóstu því að vera allt tilbúið þar.
Það er ekki beint hlut á kennsluefninu mínu.
Nei, það er bara svona...
Hljóðvinnslan, sko, en það á að vera hægt í Pygame að gera alla svoleiðis hluti. So just out of curiosity again, how many non-Icelandic speaking students am I talking to today. Okay, cool. Just because I asked the first time, I want to see if you're still there. Make sure that my English is cutting through enough that you don't just stop showing up.
It's all good.
Thank you. All right. I think I will switch over to here. Okay, so out of the problem we started with, which was how can I check if this object has hit another object, and then if it hit it within the kind of confines of the particular frame that I'm rendering now, how do I want to change its direction so that it bounces off the other object rather than just floating through it, which doesn't look cool in computer games. So we've kind of solved the second part of that, right? Like the bounce part. Like if I have checked that this actually hits another object, as long as I have a nice way to calculate the normal, or that I actually have the normal. So usually if we have polygons or lines, we just have a normal to them. If we have something like a sphere, it's easy to calculate it by just subtracting the point where we hit from the center of the sphere or center of the circle. So then we have a normal, and then I can simply say, I have the direction that I hit in, and I have the normal, and now I just have this nice little formula. I'll just write it up again on this board here so I can just store that. This nice little formula that the reflected vector equals the original vector minus 2 times the dot product of the two vectors times the normal, as long as the normal is normalized, as long as the normal is unit length. If it's not unit length already, then we have to divide. Then we have to divide by basically n dot n, which is the unit length, the length of the vector squared. So here's a question actually, this is interesting. If I don't have unit length vectors, which would be more efficient in a program to calculate my formula in this way, where I say the length of the vector squared here, or to make sure that they're unit length first and then use them in the calculation? Does it matter? Yes or no? Does it? Does it not? So what would I have had to do to make this vector unit length? I would have had to calculate the distance, calculate its length. And I would have had to calculate its actual length, which means I square each of its dimensions, and then I take a square root, right? And then I divide that up into each dimension of this vector n, and then I can use it unchanged. However, if I don't do that, and instead just calculate this with it unchanged, it's all the same calculations here as it would have been with the other stuff, except without calculating its actual length with the square root, and then dividing it into all 3 dimensions here, if we're working in 3D. If I instead say I'm going to divide by the length squared, I don't have to take the square root, because by simply taking the dot product of the vector with itself, which is basically squaring each dimension, I've already got the length squared, so I don't have to take the square root and then divide it into each dimension here and then again calculate it. Instead I can just do the dot product, which is much cheaper than the actual length with the square root, and I only have to divide it once instead of having to divide it 3 times, once with x, once with y, and once with z. The point of me saying this is not telling you, one way or the other is better, or you have to have this formula in one way or the other. It's more, if you can have them unit length without having to actually make them unit length every single time. If you can just say, I can somehow store these unit length, or I can calculate their length at the beginning of my program, and then every single frame I use it, then this would be better. If, however, I can't do that, and instead I have to calculate their length every single frame, then it's probably better to leave that out and just do the length squared in the end. Main reason for me saying this is just let's kind of be open for these kind of things when we're programming this. Like looking at every division that we do and every square root and every length that we do and think, could I have done this fewer times? Could I have done this at the beginning of the program, stored it, and then always used it and saved my program a lot of time? Or do I have to do it like this? And the reason it really matters is because we're doing these calculations every single frame. We want these frames to happen like 50 times per second. We might be doing them for every single vertex and every single polygon, which might be tens or hundreds of thousands, or even for every single pixel if we're doing things in the fragment shader. And then we might think like, can we somehow get these things unit length into the fragment shader rather than having to calculate its length inside the fragment shader for every single pixel and every single polygon in our program. However, that was a side note. Here we have the reflection. Let's go back to the other side of the board and start thinking about the other part. So if we're looking at these different representations here, and I'm going to say we basically have two lines. We can represent each line on each of these forms. We can imagine that we're just given two lines and both of them are on 2-point form. We can change either one of them, either to point normal form, we can change it to the ray, or we can leave them as 2-point form. But we have two lines, and what we want to do is we want to calculate where they intersect each other. So we have two lines, and we want to find this point here, where one line hits the other line. So where do these lines intersect? The first question we kind of have to ask each other, or ask ourselves, let's say, is like which forms would make it simplest for us to try to set up one equation that involves both of these lines. Like if we have two lines both on parametric form, both parametric rays, we can kind of try to solve for some parameter. But if I have another line here that starts in B and it's going in the vector D, then this point where they intersect is obviously some parameter less than 1 for this line, some parameter greater than 1 for this line. So now we have two parameters. So again, we suddenly have two unknowns, two parameters that we have to solve for. But we kind of want to find just one time. We want to find out when does this happen in kind of the motion of my computer game, like in my time unit scope. Like the scope of the time units that I decide are the length of a frame or the length of a second, you know, delta time, milliseconds per frame, something like that. I want to find the time when this happens. So it's kind of hard to do it if both of them are in parametric form. However, we already feel that it would be nice to find the time when the intersection occurs, both because we're doing this in kind of as parts of motion in a computer game, and also because it's just nice to have a parameter that we can solve for. And once we solve for that, it's easy to just put the value on that parameter into our formula and get the position where the collision happened. So the time where the collision happened, it's easy to calculate from that the position where the collision happened. So I would say it's very nice to have at least one of these lines in parametric form. But which of these forms seems that it'd be simplest to try to mix together, like stick a parametric form into one of the other forms, like the point normal form? Does it seem like there's a way to take a parametric form and stick it somehow into the point normal form and then just solve this equation? Does that make sense? Like there's even an unknown here, r, right? So the point normal form basically says if some point r is actually on the line, then this equation is true. Can we somehow take this function and just stick it in its entirety into R and say anything that comes out of this function is on our first line. So if I stick this function in here, I know if I can solve it as 0, then the value that I put in here is also on the second line. And if I can solve it for 0, then I know it was on the first line because I used the formula for the first line, the function for the first line. And if I can solve it for this line as well, then I know I've found a point or a time where the lines intersect, because that would be the point that is on both lines. Does my argument here make sense? Let's draw it up a little bit on the other board. So I'm going to set one of these up as a parametric form for array. Also, this is nice because we're thinking about our objects in this way. They have a current position, they're moving in some direction. So this is nice. This is my object. I'm going to imagine now that my object has no size. It's just a point. I have a line here, which is represented by some point B and some normal n, which is perpendicular to this line. So the point that I'm looking for, let's call it P hit, the point where this ray hits this line, it should be a result from the function for this, that is P of t equals A plus t times c. This function for some t should yield this point, and also this same point, we should be able to put it into this line here, which is basically n dot some r, which now is P hit minus B equals 0. So this formula should be true for P hit, right? Because it's on both lines. If it's on both lines, it's on this line, and then this should be true for it. If it's on this line, then we know that there is some t that will yield that result. So we're going to call that T hit. And we're going to call this P hit. So P hit equals A plus T hit times C. So now we're looking for a particular value for the parameter, not just some t, but T hit. So P hit equals A plus T hit times C, and n dot P hit minus B equals 0. So can I somehow just, I'm going to set this up without using P hit. I'm actually going to stuff this in there. So how would that look? N dot, give me something, please.
A plus t times c minus b.
Okay, n dot A plus T hit times C. Let's just put parentheses around that. Minus B equals 0. Now we already know that a point minus a point is a vector. We can do the dot product of vectors. We can kind of just mix this a little bit around so that points keep on being points and vectors keep on being vectors. We can use some of the rules that we already have. So we have n dot. Now here we have a vector, and A minus B would be a vector. And we can use rules about vectors and subtracting vectors and adding vectors and scalars to end up with n dot let's see, A minus B plus T hit times C equals 0. Can we split this dot product up as well? How would that look? N dot A minus B plus N dot T hit times C. Does this make sense? Equals 0. Okay, I'm trying to solve for T hit. How can I continue this to actually solve for T hit? I want to end up here with T hit equals some stuff. So I can say n dot T hit times C. Well, where could this T hit also be? Can you just take it completely outside? I want to divide by it, or I want to kind of lose the rest in the end. So I'm going to take this part here. I'm going to change that to T hit times n dot C equals, and if I move this over the equal sign, what am I actually doing? I'm subtracting this from both sides, right? The way equations work. So I could say this equals minus n dot b minus, no, sorry, a minus b. Kind of gave you the answer there. How can I lose this minus here? Just change a minus b to b minus a dot b minus a. All right, now I can finish this. How's it going to look? T hit equals
N dot B minus A divided by
okay,
N dot C.
exactly. N dot C came out there, that's below the line, N dot B minus A. So this formula seems to be taking the vector between B and A, taking the dot product of that and N, and then dividing that with the dot product of N and C. In this case, there's no kind of nice graphical way of trying to explain how that actually works. Doesn't matter. We did the math. This is what we get out. So I've found T hit. I've found when this collision happens. How do I calculate where this collision happens? So if T, let's say this is the first part here. The reflection is the last part. The first part is when did this happen? N dot B minus A divided by N dot C. How do I find where this happens?
T hit times the vector.
T hit times the vector C plus A, right? It's here, P hit equals A. So that's my P hit, that's where it happens. I simply put it into the parametric form for the ray. So it's just there. So I figured out when this happens. If this is in a computer game, in which cases would I actually calculate this? Like, I first have to look at T hit and decide, is it worth continuing? Let's say my units are seconds, and I have an object that has its current position here in A, and C is the amount it will move in a second. So 1 second later it'll be here. In my program, we have a way to calculate what I've called delta time, which is basically the elapsed time since the beginning of the last frame to the beginning of this frame. That's kind of, I'm calculating for this time. I'm saying this next frame needs to imagine that it's that long because I need to make sure that everything happens at the correct speed. So if the last frame took this long, that's the amount of motion I have to incorporate. But I still use seconds into that. So then I basically have to say, all right, I find T hit. Then I have to say if what T hit is less than what? Now, if it's less than, in this case, I'm in my program, I have these time units. So t is a time variable, delta time. So we can write it like this, delta time, delta t. So that's the elapsed time since the last frame. So I'm basically saying if it happened within this frame, is this enough? How would I draw an image for a t hit that has a value that's lower than 0? What would that image look like? I'm going to draw my A here. I'm going to draw my C here. Where would the line be if this formula yields a t hit that's lower than 0?
Does it go through the...
Yeah, it's already gone through. It happens in the past. So a minus time happens in the past. I'm not interested in that, right? So if t hit is less than delta time, what I'm interested in is this is where I was at the beginning of this frame. This is where I'll be at the end of this frame. That's the scope I have. I don't care what happens in the future, because someone might push a button and my spaceship might take a turn and then it's just going another direction, and none of this even matters. Only thing that matters is, does this happen from the time when I started rendering this frame till this time when I end rendering this frame? So between 0, t equals 0, and t equals delta time. If in a program, obviously, this would be delta time. So my if sentence has to be expanded to say, and, is it uppercase or lowercase in Python? Lowercase and t hit is bigger than or equal to 0. Then I'm interested in more stuff. If this happens, then I have to calculate where this happens. Or in some cases, I might not even be that interested in that.
Do we have to have the equal there?
It's less than delta time. This exact moment in time when your frame begins or when the next frame begins has to be included, because there is a tiny chance that you get right up to that point in this frame, and it doesn't happen because I said if t hit is less than delta time, so it doesn't happen there. Then in the next frame, it's also right there, and so I miss the 0, and it doesn't happen. So yes, there is a chance. We either have to have the equals here, or we have to have the equals here. It doesn't matter on which side it is. The likelihood of you encountering a problem in your actual program, if you forgot to have the equals, slim. The likelihood of someone encountering the problem once you've tested it and then sold it in 1 million copies, 100%. So I'd have the equals on both sides, in fact. That's what I do, because again, this is computer games, or in my case, I'm always thinking about computer games when I'm thinking about graphics. And if it looks correct, it is correct. So we're not doing real world physics, we're not doing actual, not in my case anyway, but a lot of you may want to do graphics for actual real world perfect physics. So my rule is basically if it looks smooth and it looks cool, then it's what I want it to be. So I would just put the equals on both sides to be safe, to make sure that you don't, in a really important run of the final boss in some game, someone out there in the world kind of slides through something that he was supposed to bounce off. You don't want that to happen, so be safe rather than sorry. But for it to be correct, have the equals on one of them. Either one is good, doesn't matter. And then also, I've programmed these kind of things into computer games where I thought one frame backwards. So I was thinking not t hit is between delta time and 0, but between 0 and minus delta time. And that game completely worked. I was just thinking the same amount of time backwards rather than forwards. It just depends on what you feel comfortable with programming and how you feel that your program kind of works and is correct. So, we have the time of impact, we have the position of impact. We have 10 minutes left of the class, right? That's perfect.
Actually, question.
Yes.
If you would have that situation where you're just on the point, like where it's t hit equals delta time of that, would it be like you would go into this if sentence like right then and there because t hit equals delta time, and then on the next frame you would go into that because t equals 0?
Huh. Yeah, okay, that's true. So
If you had them both.
this kind of depends a little bit on what I'm going to talk about next, but yes, this would happen. I'm here, and inside this frame I go exactly to here. So in the first frame, it doesn't equal delta time. No, it's not less than delta time because it equals delta time. So
Yeah, but if you would
okay.
equal
Yeah, true.
both of them.
So if I put equals on both of them,
Yeah.
it would happen here, and I would change my vector, and my position would be right here because I ended right there. There's no extra movement left. In the next one, yes, it would equal 0 again, so I'd bounce and I'd go through.
Yeah.
So both would send me floating through, neither would send me floating through. So we have to have them on one but not the other, but it doesn't matter on which one. Good call. And this brings me perfectly to an idea. I kind of want to get a little bit more room here. So, a more complicated collision response. But I'm going to incorporate all of this. I'm here, and my vector goes somewhere to here, and I would end here considering this particular delta time. So, at t equals 0, I'm here. At t equals delta time, I'm here. At t equals t hit, I'm here. This means this has happened. I've gone into my if sentence. I'm going to change my vector according to this formula. This is all on the screen, yes? So my current vector is here. My new vector will now be the reflected vector here. So this is my new vector. Where do I go? What do I make my current A? Like, do I set it to what it would otherwise have been? Probably not, because I don't want to go through. Do I set it to P hit, which is here? P hit, do I set it just to exactly P hit? That would actually mean that I'd have to have the equals on delta time, because if I set it to P hit, then I'd equal 0 next and bounce through. Do I set it to P hit? Do I calculate times delta time from here, out from here? Like, what's the most exact thing to do? Use P hit. So use P hit. So I go back to exactly where the collision happened.
Calculate from there.
And calculate how much from there. Do I calculate my full delta time from there? Like the frame started here, but the frame did start here.
Delta time minus t hit.
Yeah, so delta time minus t hit in this direction. So I change my vector, I calculate the reflected vector, I go to p hit, and then I recalculate, but not with the full delta time, but with delta time minus t hit. What could happen now? What could have happened in this? Let's imagine that this is a wall here. It's part of some big old monstrous thing that I'm bouncing around in. What happened here? I was here. I should have gone here, but this collision happened. I change my direction, and I only take the rest of the frame, and I go through here. Okay, if I just stopped at P hit and decided it's okay to waste the rest of the frame, I wouldn't have to recalculate. But the correct thing to do would be to take delta time minus T hit, recalculate, but that means I have to do my collision detection and collision response. So in that case, my whole collision detection and collision response for this object would have to be recursive, and it would not stop until what? Like, when can I say I don't have to do this again?
They went all the delta time.
Yeah, so when I manage to go the whole delta time, in this case I'd have another here, probably bounce to here, have another here, then I'd go here and I'd end up here. So I would have to recursively do my entire collision detection until no collision happens. And I'd have to do it for this particular object that's moving, but for all of the objects that it might run into. So hopefully we have some way of kind of throwing away objects that are far away and not having to do a full collision detection with all of them. But that would be the correct thing to do, to actually reiterate on the collision detection until no collision happens, and then I'm done. In the vast majority of frames, how many collisions happen? Like if you imagine playing a computer game, where you're floating in space and you once in a while hit something, dong, 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 you're bouncing. Like the vast majority of frames has how many collisions for that object? 0. Okay. When you hit something, in most cases you're going to hit and you're going to have one collision. But every once in a while you might end up in a corner like this and kind of clink. But that's okay, it just happens within the frame. So what you see as a user is in one frame you're here and you're going in this direction, in the next frame you're here and you're going in this direction. You don't see all of that because it happens within one frame. You kind of just get wedged into this corner, boink, and then you're going somewhere else. And that's fine. But what you kind of have to keep in mind is, if you want to simplify this, just leave yourself at exactly p hit, but then make sure that the less than or equals is on delta time and not on 0, because otherwise you're here and you're going to have equals 0 the next time. And then you're going to have that 100% of the time because you're actually putting yourself in exactly p hit. And exactly p hit will in the next frame yield a t hit of exactly 0. All right, so you can just leave yourself in the p hit and give yourself a new vector, and then the next frame you'll start moving along that vector. That means you're safe from this reiteration, but you're not entirely correct, because the correct thing to do would be to make sure that you move the entire delta time, that the entire time that this frame took will actually give you motion. Otherwise you're kind of cheating your objects out of a little bit of their motion this frame. This was food for thought. You just think about how you like to do this. Not everyone in their actual 2D game assignment has to do anything this complex. You can do a lot of static checks that can look just as good as a full-on delta time check like this. But if you make this work correctly, it's always going to give the most correct results. And the best thing is it's going to give the least special cases. If you do a static check, like I have this box, and I'm just going to check, am I inside it or am I not inside it? I'm not going to take the motion over time to check when it happens. I'm just going to say, have I entered this box? Then you have to take special cases. Do I believe I entered at this side or this side? You know, if I'm going in this direction, I probably didn't hit this side or this side, but I might have hit this one, I might have hit this one. If I'm right here in the corner, it's a tough call to make. Did I hit on this side or did I hit on the other side? Maybe there's another object next to it, and within this frame you go from here to here. Suddenly you're inside this object, you know, but you were supposed to bounce off here. If you do a static check, just check, am I there? All of these will become special cases in if sentences and stuff like that. If you do the full delta time, your original calculation is a little bit more complex, but when you've done it correctly, you've rid yourself entirely of all the special cases, because every single case is actually calculated from where you are to where you'll be at the end of the frame, and you'll know exactly where the hit happened. Also, multiple objects. What do I have to do to know where the actual hit happened? Let's say these objects are in an array, and this array, this is the first object in the array. So when I just do a for loop through the array, I check this object first. Then I check this one, and what happens? If I was here and I go to here, I detect a collision here. What do I have to do now? Do I change my vector as if I bounced here? Or do I store this and say, I'm just going to save this T hit and this particular collision, and I'm going to keep it until I'm finished with all of them. Then you check this one, and you find a new T hit. How do I compare the T hits? A T hit that I've already found and the T hit that I just found. How do I know if I want to keep the new one or keep the one I found already?
Keep the smallest.
Keep the smallest one, that's still bigger than 0. So if I get a T hit that's actually between 0 and delta time, I store it. If I have a stored one, I check is the new one smaller, then I take the new one and the new collision and I throw the rest away and say it doesn't matter anymore because this happened first. If I was doing it in the other direction and I found this one first, then I find this one and I see the old one is smaller, I take the new one and throw it away. And we're done with the time. Thank you very much for this lecture. See you again Monday.